Well, first, thanks to the organizers for inviting me. It's really a pleasure to be in this nice place. Also, I have to say it's the first talk without a mask that I give in the last few years, so it feels a little awkward. So I don't remember how to use my mouse and all that properly. So as Sonia said, I'll talk about polygon recutting. And polygon recutting is it's a dynamical system and was introduced by Vsevolod Adler in early 90s, 92 or something like that. 90s. And it somewhat resembles the pentagram map that Misha Shapiro was discussing yesterday. And it was actually introduced at about the same time. But for some reason, I'd say it's much less popular and much less known. And I think it's a little unfair. And I hope to convince you that it's probably as fundamental as the pentagram map. So first of all, I'll start with a definition. And okay, so polygon recutting, it's a dynamical system, as I said, and it's a dynamical system that lives on planar polygons, although later we'll actually need to generalize to a higher dimension. So this one starts with a polygon in the plane. And so the setting here, it's not projective, because Misha yesterday was talking about projective polygons. Here we consider a polygon in the Euclidean plane, and then we do the following operation. So we choose a vertex of the polygon. We take two neighbors of the vertex, they form a triangle, and then we cut off this triangle from the polygon. And after that, we flip the triangle. So we kind of remove it from here and turn it around like this, and then glue back along the same diagonal we cut it. And as a result, we get just a symmetric copy of this triangle. Another way to think of it is, so it's just a reflection in the perpendicular bisector of this diagonal. Probably recutting is not a very great name. I think it's a kind of a lost in translation kind of problem, because it's more reglued than recutting. But I think that happened because probably Vsevolod wrote his paper in Russian, and then it was translated by someone, and it became recutting. Anyway, so, and we will think of it as a dynamical system. And of course, if we do this thing at one single vertex, there's clearly no dynamics here, because it's obviously an involution. If you do it twice, just get the same polygon. But instead, we're going to allow this operation at any vertex. So if this vertex has index I, we'll call this operation here rho I is recutting at the vertex I. And then what we do, we basically allow recuttings at any vertices, and we can repeat these recuttings. We can do them any number of times in any sequence. So in other words, we consider the group G that's generated by this recutting. So if we have n vertices, the group generated by recuttings from 1 to n. And well, that's our dynamical system. So it's not quite a dynamical system from the conventional point of view. So there's no single map that we take and iterate, but instead we have a whole group action. And that's our dynamical system. And basically, well, I wrote a paper on this just recently, and the main result of the paper is that this is an integrable action. And I will explain what it means, and I'll say a few words about the proof, and also about the relation of this with things mentioned in Misha's talk and in Rick's talk, so cluster algebras, the dimer model, and things like that. The main result I can formulate right away. So the main result is that this is an integrable system, and so as I said, we consider this the action of the group G, and the actual space of this system we want to consider it's polygons in the plane moduli isometries. So we don't distinguish between polygons that are isometric to each other, and the claim is that on this space, this is an integrable system. So the G action on polygons mod isometries is integrable. And well, the definition of an integrable group action, yes. No. Well, as a reflection in the perpendicular bisector of this diagonal, I guess. Yeah, that's okay. That's really, I mean, a polygon is just a sequence of points. And of course, well, as usual with these maps, it's only generically defined. There are certainly situations. So if these two vertices coincide, then you are in trouble. It's a birational map, as like, well, most discrete integrable systems that we know. So the claim is that this is an integrable system. Basically, the definition of an integrable group action is pretty much the same as the definition of an integrable map. So here, well, the claim is that there is certain number of functions on the phase space that are invariant under the action. And then if we look at the joint level sets of those functions, then the connected components are tori. And well, I'd like to say that on each torus, the action of the group is given by translations. That's not quite right, because on each joint level sets, we have several tori, and in general, the group elements, they may jump between different tori, but there are finitely many tori. So the actual claim is that if you fix an invariant torus, there is always a finite index subgroup in G that's given by translations on this torus. That's the definition. And this, by the way, implies that, well, for complicated groups, that's just impossible, because, well, basically we should have a finite index commutative subgroup in our G. So if G is sufficiently non-commutative, then the action cannot be integrable. And this is something that was noted by Alexander Veselov in one of his first papers on discrete integrable systems. And in this case, it's actually quite easy to describe this group. So the relations satisfied by these generators, they are precisely the relations of what's called affine symmetric group, or affine Weyl group of type A. So these are involutions, and if you multiply rho I and times rho I plus 1, then this product is an order 3 element. In particular, it's well known that this group, it's not abelian, but it contains a huge abelian subgroup that's of finite index. So this is the main result. And well, just to give you some examples. So let me say what the dimensions of this tori are. So there is a general formula that I cannot remember, but it's quite easy. I'll just give you examples and then you can interpolate. So if you consider triangles, then we have 0-dimensional tori, because the triangle, you can just get a triangle and its reflected copy, and that's the whole G orbit. So here we have 0-dimensional tori. For quadrilaterals, it's actually also 0, because it's clear that this dynamics, it preserves side lengths up to permutation, but it also preserves the area. And if you have a quadrilateral, you fix the length of sides and you fix the area. There are only finitely many such quadrilaterals. Because of that, you have finite orbits for quadrilaterals. So for quadrilaterals, it's also zero-dimensional orbits. And then it goes like 1, 1, 2, 2, and so on. Yes. Well, you can define, there is a notion of signed area for arbitrary polygon. So a polygon is just a sequence of points. And then there is, you can write a formula that produces actual area for convex, and then it is kind of signed area when you, I don't know, here you will count some parts with a positive sign, some parts with a negative sign. There is a certain orientation rule. Yeah, you can integrate x dy along the boundary. And you just orient the boundary in the direction of increasing I, and you can integrate x dy or y dx or something like that. So, yes. No. So not quite. I mean, for a small number of vertices, indeed, the integrals are the length of sides and the area, but as n grows larger, that's insufficient. And so these are dimensions of this invariant tori, but not all the integrals are of the simple geometric nature. I think if you go up to 6, then all integrals, they have a very simple geometric interpretation. Yeah, for 5, it's still like length of sides and the area. For 6, it's also that. And also if you add up angles at every second vertex, that's also preserved, as easy to see. That's sufficient to integrate this dynamics on hexagons. And then when n is 7, that's already insufficient. So that's, and here you just interpolate this sequence 0, 0, 1, 1, 2, 2, and this formula with n divided by 2, 4, something like that. I'm not good in producing such formulas. So then it goes like 2, 2. So that's not quite a dimension of polygons with fixed side length and area. That's actually much smaller. So here, what happens is that we are used to thinking of integrable systems is that they have tori, and the dimension of the tori is approximately 1/2 of the dimension of the phase space. Here, it's actually not the case. So here, the dimension of the tori is approximately 1/4 of the dimension of the phase space. So it's much smaller than what we're used to. And so one last thing I mentioned about the theorem before I proceed. So that's not quite Arnold-Liouville integrability here. So this is the setting in this theorem is actually of non-Hamiltonian integrability. So there is no invariant Poisson structure. If you want to find invariant Poisson structure, you need to extend the space of polygons to some kind of twisted polygons, similarly to what Misha was describing yesterday. If you want to closed polygons, then one can prove non-Hamiltonian integrability. Or, well, one could still find some kind of a Poisson structure here, but it's actually a Dirac structure. It's not quite a Poisson structure. It's a Poisson type structure with presymplectic leaves. But it's really not needed here because one can first prove integrability on the bigger space and then prove non-Hamiltonian integrability on the smaller one. All right, so this is the main result, that this is an integrable system. And I should say that, so the final proof of this is in my paper, but some ingredients of they were known before. So some results on integrability of this system are by Vsevolod Adler himself. And then Sergei Tabachnikov also worked on the so-called discrete bicycle transformation that's close to this. So some results can also be extracted from Sergei's paper. So some things were definitely known before. I just collected all these ingredients together and I finalized the proof. So, and now let me explain. So there is a quite nice and simple construction of the invariance for this G action. So I want to explain that. And after that, as I said, I'll a little bit about relation with cluster algebras and all those things. So invariants here are very easy to construct, but to construct invariants, for some reason, it's better to think about the three-dimensional system rather than two-dimensional. And the definition in 3D, it's more or less the same. Well, when you cut the triangle and then glue it back, clearly there is no unique way to do it. But if we use the other definition, the reflection and the perpendicular bisector, that works fine. In 3D, if you have a polygon perpendicular bisector to this is a two-dimensional plane, you can reflect the vertex in that plane, that works. It's actually another way to state this. In 3D, you cut this triangle, then you glue it back with an opposite orientation and also with a requirement that it stays in the same two-dimensional plane. So clearly there is an analogous system in any dimension, but actually this result only applies to dimension 2. I don't have a proof even for dimension 3 that it's integrable. One would think that these are very similar systems, but somehow I believe they are very different, and I'll comment on that later. So in the 3D case and the 2D case, they're different from each other. So I'll use the 3D system to construct the integrals, but the integrability proof is actually only for 2D. And of course, the 2D system is a restriction of the 3D system. So if I can construct integrals in 3D, I can then restrict them and get integrals in the two-dimensional set. So now we have a polygon in the three-dimensional space. And for the polygon, so I'm gonna look at the edges of the polygon, and I'll think of them as vectors connecting neighbors. And actually, instead of thinking of them as vectors, I will think of them as quaternions. And this will be, I will identify R3 with purely imaginary quaternions. So this thing, I'll write it as a span of ijk. It's a quaternion, and then I can associate such a quaternion with every edge of the polygon. Let me call them qi plus 1, and so on. And then one can notice the following thing. So let's take, okay, that's bad. So it's qt and qt plus 1. So let's take two adjacent edges and let's multiply these two quaternions together. So I multiply qt and qt plus 1. So I guess everyone knows how to multiply quaternions. So this product will have a real part and imaginary part. The real part is the scalar product or inner product, and the imaginary part, yeah, that's right. Thank you. And the imaginary part is the cross product. And then the claim is that when you do this recutting operation, so when you replace this with a reflected copy of this triangle, then this clearly doesn't change, because this this inner product here, it's the product of magnitudes of these two things times the cosine of the angle. That doesn't change. Angle is the same here, while the magnitude is also product of magnitudes times sine of the angle, same thing. And the direction of this is actually the direction of the two-dimensional plane containing these two vectors. By definition, that doesn't change. Therefore, this product, it stays the same when we multiply, when we apply this operation. And well, oh yeah, and another thing I didn't mention that's also important. So the product stays the same, but the sum also stays the same, because the sum is just this diagonal. Here also doesn't change. So qt plus qt plus 1, it also doesn't change. And well, now it's super easy to construct integrals, knowing that this kind of symmetric functions stay the same. So saying that the sum is preserved and the product is preserved, I believe it's the same as saying that this polynomial here is preserved. And so in other words, when we do recutting, so if we had the qt and qt plus 1, they will be replaced by qt plus 1 prime, and these two polynomials, they are equal to each other. It looks a little strange because it seems to contradict the fundamental theorem of algebra. It looks like this quadratic polynomial has 4 roots, but that's not true because quaternions are non-commutative. So when you write a polynomial like that, only the right factor gives you a root. The left factor, it's, well, it depends on your notion. There are right roots and left roots. So this is a right root, this is a left root. So this polynomial still has 2 roots. This is one of them, this is another. 2 right roots, and then there's 2 left roots. So that's basically, that's an algebraic description of this recutting operation. This is an equivalent thing. So if we have this relation, that's completely equivalent to recutting. And then, well, since we want to allow recutting at every vertex, we just need to multiply all monomials like that. So we look at the product z minus q1, etc., z minus qn. And this is preserved by all generators of our group but one, because there is a bad situation when we recut at a vertex that's in between these 2 edges. Then this is not quite preserved. But up to, if we allow to permute this thing cyclically, then it's fine. So this means that up to conjugation is preserved. So here we can consider the algebra of these polynomials over quaternions extended to a field of Laurent polynomials, and there we have conjugation. Up to the conjugation, this polynomial is preserved, and that's basically where the first integrals come from. So now we just consider functions on quaternions that doesn't change under conjugation, and everyone knows what they are. The real part of a quaternion is invariant under conjugation, and the absolute value is invariant under conjugation. Take absolute value of this. Absolute value gives simple calculation. It just gives side lengths. So these are integers that we already know. They're preserved up to permutation. But then if you take the real part of this, this produces something non-trivial. It produces the area in particular, but not just the area, because, well, when you take the real part of this, it's still a polynomial in Z. And one of the coefficients of that polynomial is some function of the area, but then there are some higher things, and they're, well, something that it's not clear how to describe geometrically. But the claim is that, well, this is sufficient. So that's sufficient to prove complete integrability. And, well, of course, it doesn't quite conclude the proof, because one needs kind of a Poisson structure here, show that these integrals are in involution. Also, one needs to show that there are sufficiently many. And for the Poisson structure, there are, well, at least 2 different approaches here that I know. So one approach that I actually use in the paper is to use this kind of a refactorization structure here. So as we describe the map, it's basically sort of flipping the factors in a polynomial. And because of that, it's natural to introduce a multiplicative Poisson structure on those quaternionic polynomials. And then, well, it's not hard to do that. And using the multiplicativity of that structure and this description of the map, it follows that, well, the map preserves the Poisson structure. And then the integrals Poisson commute, basically, because that Poisson structure is given by an R matrix, and then we are taking central functions. So central function. That's right. So it is Hamiltonian on a slightly bigger space. So you first extend the space. So already here you see there is a problem when we introduce this QIs. QIs are edge vectors, and then if you have a sequence of edge vectors, it might not close up. So because of that, we extend the space of polygons on a slightly bigger space. There is a Poisson structure. Everything is fine. It's classical integrability. But then the space of closed polygons is just not a Poisson submanifold. So on that subspace, well, the dynamic reduces and the Poisson structure not quite. You could still reduce it as a Dirac structure if you like. That's quite useless, honestly. So it's much easier to prove integrability using this non-Hamiltonian approach. Just when you show that have some number of first integrals, some number of vector fields that commute with your dynamics. In a sense of Lie, yes. So that the number of conserved quantities plus the number of conserved vector fields is the dimension, yes. Because that kind of integrability, it's basically usually it's inherited by invariant submanifolds. Assuming that they're invariant with respect to this vector field and your dynamics. While Poisson structure, sometimes it doesn't. As I said, well, in principle, one could still restrict it as a Dirac structure. It's just quite complicated calculation, and there is really no use in it. I mean, integrability, you don't really need Poisson structure to prove integrability. You need this vector field and integrals, yes. No, it's not obvious, but it's quite easy to prove here because basically by construction, integrals are given by a real part and absolute value of a quaternionic polynomial. So independence of integrals basically means that the map given by integrals is kind of an onto on an open set. So what you need to prove is that given two polynomials of certain degree, you can find a quaternionic polynomial with given real part and given absolute value. That's pretty simple algebra. You can construct it explicitly. You don't need to differentiate anything here to prove it. Yes. No, you can find solutions here, sure. I mean, but you can find solutions here for a different reason because you can also show that it's algebraically integrable. It linearizes on a Jacobian of a spectral curve. So finding solutions here in principle is possible. I guess it's a little hard to do explicitly because you have this huge group, and then for each generator you need to kind of describe how it acts. But yeah, I think it should be possible. So, but there's no need to use Lie's theorem here to find solutions because it's algebraically. But I mean, I didn't prove, I didn't obtain formulas for solutions, but I think it's not possible. Does that answer your question? You don't look. Okay, so I mean, we can discuss later. That's okay. Okay, any other questions on this part? Yes. Well, any. Yeah, sure. Well, and in these terms, like closed means that the sum of these q's is 0, so it's one of the coefficients. Well, but any quaternionic polynomial factors, it's into linear factors. Of course, there is a little issue here that the real parts should be 0, but that's also easy to kind of guarantee that that's going to be the case. So it's pretty much arbitrary quaternionic polynomial can be written in this form. There should be a certain assumption on its real part. I think that guarantees that the real parts of this roots are 0. So, but in how many ways? N factorial. Well, typically there is an issue there because there are different kinds of roots for quaternionic polynomials. There are roots that are just like usual roots, but then there are roots that are called spherical when the whole conjugacy class is a root. But if you count things in a right way, it's n factorial roots basically. But it's like for a usual for a usual polynomial, you have n factorial factorizations, and they're just the same up to swapping factors. But here, when you swap factors, this factors change. But you still have. You ask how many factorizations, right? So yeah, typically n factorial. Yes. Unless something degenerate happens. Yeah. The order of the group is no, it's an infinite group because it's an affine symmetric group. It's the order of the, well, this group, it can take huge abelian subgroup. If you take quotient, then you just get symmetric group, and that's the order of the symmetric group. But yeah, basically this group, it does kind of interchange factors here, but because of this, there is this cyclic structure here, and because of that, it's not quite a finite group. If you weren't allowed doing the cyclic permutation, then it would be just a finite group interchanging factors. And because you allow things to go around, it's actually an infinite group. Okay. So now, so as I said, it's not hard to construct a Poisson structure here using Poisson Lie theory, and that's kind of the main approach I take in the paper. Now I just wanted to briefly mention another approach to this, which connects this to cluster algebras, and that also gives a Poisson structure, and it can also be used to construct first integrals, for instance, using a dimer model construction that Rick mentioned yesterday. So, well, cluster algebras were discussed a lot yesterday, so I won't go into details. Basically, well, it's something that, and I won't care about cluster algebras themselves here. It's more about the kind of the Poisson part of the picture. So basically, if you have a quiver, which is a graph, then you put variables at the vertices of the quiver, and you consider a space whose coordinates are those variables. And then there is a standard Poisson structure that one can associate with it. It's just a very simple log canonical Poisson structure whose matrix is basically given by the adjacency matrix of this quiver. And then there are these cluster mutations performed. You choose a vertex, and mutation at a given vertex, it somehow changes the graph, so you get a different graph. And then there is another graph here, and you have a certain transformation rule from variables sitting on an initial graph to the variables sitting on the new graph, and the main property is that that's a Poisson map. So these cluster transformations, they can be thought of as Poisson maps of certain kind. But because the graph is different, it's a Poisson map between two different spaces. So you have a space associated to one quiver, a space associated to another quiver, and there is a Poisson map in between them. And that's not quite what we want, because if we want to build something like, well, which we hope to be an integrable system, then we need a Poisson map from a space to itself. And because of that, one needs to find a sequence of cluster mutations that recovers the initial graph. And that's a Poisson self map. And then there are constructions that for certain quivers, they allow one to prove that that's actually an integrable map. And in this case, so we need such a sequence of, so to find such a sequence of mutations that recovers the quiver, I'm going to use the construction called the twist of a quiver, and that was introduced by Pilavsky and Galashin a few years ago. So that construction, it's so because when you start with an arbitrary quiver, it's just absolutely not clear how to find sequences of mutations that recover the quiver, because a mutation is some changes the graph in some complicated way, and then you don't know whether you can mutate several times and come back. So this twist construction, it constructs kind of a starting with a quiver, it constructs a new one which always has this nice sequences of mutations. I think it is. Yes. So I'm not certain that. Well, okay. So I borrowed the name from Pilavsky Galashin paper. I'm not certain that's the first time it appears. Sure, that particular examples of this one. Yeah, sure. Yeah. So twist is this. So you start with a quiver. So it's an operation you apply to a quiver. So let's say we have two vertices of a quiver. So for all vertices of the quiver, we keep those vertices, but we also create their copies. So it's a kind of a double of a quiver. And then if this were connected by an edge, these are also connected by an edge. But then we add additional edges that go from old vertices to new ones, but they go in the opposite direction. So here we had an arrow like this. So we add this arrow and we add this arrow. So and you do that for every arrow in the quiver. So that's what a twist is. And I might be wrong about the source of this construction. Well, actually, when I found a quiver for the system, I even didn't know that it's called that way. But then I looked at that paper and I saw that they called it a twist, so I used that name. So I'm sorry if historically this is totally wrong. So and then, so for this, so to construct a quiver for this recutting system, we start with a quiver that's just a circle with arrows. So it's the Dymkin diagram of affine AN type. And then we perform a twist of that. So we get, well, something similar to what's drawn here. It's two circles with arrows and arrows in the middle going in the opposite direction. So that's the quiver that we'll use for this system. And we need to put variables at vertices. These variables, they should somehow be related to recutting. They should have the geometric meaning. And this time, so again, so now we consider the planar case. So we're no longer considering the 3D case. So in the planar case, we again look at edges. But now we're going to view edges not as quaternions, but as complex numbers. So now these two edges are complex numbers, and for every vertex, one can compute the ratio of two corresponding complex numbers. And let me call them yi or yt. So, and then the variables that we put on the quiver, they are this yi's. So yi's are the ratios of consecutive edges of the polygon. So these are the cluster variables for the system. And at the copies of these vertices, I'm going to put yi bar. So that's the complex conjugate of yi. It's a little bit, the setting here, it's a little non-standard because usually one thinks of cluster variables as dependent. Here, they're not quite independent because they're complex conjugates of each other. But that just means that we're considering a real slice of some cluster system. And it's a non-standard real structure because standard would mean that we just put real numbers at vertices. Here instead we require that, well, variables sitting at certain vertices are multiplex conjugate to each other. So it's a different real structure. And yeah, I didn't say a very important thing about this twist. So why the twist nice? So the thing with a twist, so if you mutate one vertex, then the quiver changes in some rather complicated way. But then you mutate at the copy of the vertex, and after that second mutation, the quiver again becomes the same as it initially was up to permutation of these two vertices. So then you just relabel them and you recover the quiver. And it's a nice construction because it sort of starting with any quiver, you can produce a new one which has this sequences of two mutations that recover the initial quiver. In particular, it's a large source birational Poisson maps. You can start with any quiver, consider its twist, and it gives you, well, a lot of birational Poisson maps that are just given by this sequences of two mutations followed by permutation of vertices. And here, well, the description of recutting cluster terms, it's exactly like that. So we have vertices where the yi variables sit, and we have vertices where yi bars sit. So we mutated yi, then we mutated yi bar, and then we interchange those two vertices. And that just an explicit verification at the level of formulas that that's equivalent to the recutting operation. So in particular, it follows from that there is a Poisson structure that's invariant under recutting. It of course does coincide with that multiplicative one that I was talking about before. There are many difficulties here though, because all this kind of different variables that we're using, they're all living on slightly different spaces. So one needs to connect the spaces. So in particular, when we use this yi's, so we mod out not just by isometries, but we can also rotate. No, rotation is okay. We can rescale, and we modded that out. So there is one dimension lost here, but well, still, this gives an invariant Poisson structure, and I think I still have 3 minutes. And in principle, one can also use this cluster description to find invariance, because as one can probably see from this picture, if you look carefully, you'll realize that this quiver can be drawn on a torus. Because what is drawn here, it's an annulus, but you can think of this annulus as a projection. So think of a torus which you project to a plane, you get an annulus. So there are arrows here that cross, but on a torus you can clearly uncross them by putting some of them on the kind of upper part of the torus and some of them to the lower part of the torus. And then one gets a quiver on a torus, and that's, well, kind of exactly the situation where one can apply several different techniques to prove integrability. So one approach is to use the Goncharov and Kenyon setting with a dimer model on a bipartite graph. And the idea is that you look at the graph on a torus that's dual to the quiver, and you play the dimer model game on the graph, and that gives you first integrals. Another approach is to use this networks that Misha Shapiro was describing yesterday, and that also gives, well, that basically gives you the same integrals, just the different combinatorial techniques, but the result is the same. There is a little issue here with this approach. So if you draw this graph on a torus, you'll see that the dual is not quite bipartite. But in order to fix this, one needs to add some arrows to this quiver. Basically, you add an arrow that goes back, and that's a totally allowed thing. So you, given a quiver, you can always add these arrows that cancel each other. And after that, when you look at the dual graph, you'll see that that's just a hexagonal lattice on a torus. The dual bipartite graph is a hexagonal lattice on a torus, and the this should be compared to the pentagram map. So the pentagram map, it's a dynamical system that's related to a square lattice on a torus. And this is related to the hexagonal lattice. So that's why I said that this is probably considered as being as fundamental as the pentagram map, because these are basically two systems that are related to two most simple lattices on a torus. And my time is up, and I also said everything, I guess. So thank you. So first of all, let me say that I believe that actually, in some sense, the 3D version of this system is a non-commutative version of the 2D, just because in 2D, so cluster variables are these ratios of complex numbers. In 3D, you have this fully developed quaternions or SO3 element. I believe it's kind of modeled by the same quiver, but with non-commutative variables. I think that's right, but well, yeah, it's a non-commutative version, so that's why I say that things do not work right away in other dimensions. But I mean, one can probably use techniques from your paper with Nick and Simon. Yes, I think, but I mean that's a separate thing, and I didn't consider it. I thought it was interesting because, well, kind of, it's not a straightforward generalization, but it's a non-commutative version. But yes, I think that's. I don't know about any group, no, but yeah, probably. I don't know. Yeah, I don't know. Who was? Yes. Yes. Yeah. Yeah, there are certain problems because like you have the geometric space of closed polygons, which doesn't have a meaning, but yeah. Yeah. Yes. Yeah. Yes. Yeah, and I think this is in a way is a little simpler, just like KDVs. Yes. Yes. Yeah. So, well, first of all, your first question, before taking the quotient, whether it's integrable, I don't know. I think yes, but I don't know how to prove it. It should be easy, but I don't know how to prove it. Yeah, I mean, There are, as you know, there are two additional integrals that you have before taking the quotient, but there's some structure that's lacking in before taking the quotient, like a Poisson structure or something like that. And because of that, it's not really clear whether those two additional integrals. Well, I mean, if you can find a Poisson structure, then they should be sufficient to prove integrability, but I don't know. Yeah, so there is this circumcenter of mass that's preserved in addition to this. And then you asked about higher dimension. Well, the thing is that this construction somehow, it only works in dimensions 2 and 3. In higher dimensions, well, you should use some higher dimensional generalizations of quaternions, right? Which are, well, they exist, but they're not quite as good as quaternions, as we know. You could probably use some kind of Clifford algebras here, but it's, I don't know, feels a little weird. Integrals exist, yes, yes. And I mean, well, even as I said, even for 3D, I didn't prove that it's integrable. Integrals are the sort of the same, but well, it's non-commutative, so the Poisson structure construction is going to be different. I just didn't look at the details in that case, and I don't know if there are any difficulties with that or if it's kind of a straightforward non-commutative generalization. I don't know.
Otherwise, there won't be any coffee break. So let's take a figure again and